An exponential function is another type of function. An exponential function is a function of this type. You have a raised to the power, a is any constant, raised to the power of x. You can also write the function as more general as, for example, a, if you multiply by a constant and also add a constant. But let's keep the most basic form, this one. And we also call this exponential function. For example, an exponential function is 2 raised to the power of x, or 10 raised to the power of x, for example. So these are examples of exponential functions. How do the graph for these look like? So if you look at them in GeoGebra, and now we are skipping a normal, if you want to do by freehand, you just have to make a table and put in points in your coordinate system and then find out how the curve looks like. But let's skip that step now and just go directly to GeoGebra. So 2 to the power x, that's this curve, for example, and 10 to the power of x. Would be this red curve. So you see here a larger number in the base give a steeper curve. And if, for example, if we would have a half squared, a half raised to the power x, then instead the curve will go down. And if we have a trivial example of 1 raised to the power x, and that's a bit silly because it's always equal to 1, then we will have the orange curve. So you see, if the base here is larger than 1, then the curve will go up like the green and red. And the higher the number, the more steeply. And if it's lower than 1, the base, it will go down. So these are different examples of exponential functions. They all have in common that they grow very rapidly. So you see that they grow very rapidly. No matter if it's this green or red one, they will grow exponentially, you say, rapidly. Or decrease exponentially rapidly. So you go very quickly to go to 0. So these are an important part of exponential functions. They grow rapidly or decrease rapidly. So when can you come across these type of functions in reality? For example, if you do bank interest, loan interest, or value of a car, or half-life of a radioactive material, or bacterial growth, or a sound level, for example, you talk about decibels. All this has to do with exponential functions. So let's now take this one as an example. 2 raised to the power x. So we have, what is the function? That is, what is y equal to if f is equal to 0, for example. Yeah, then it's 2 raised to the power 0, that's 1. And f of 1, that's 2, of course. F of 2 is 4. F of 3, 8. This grows very rapidly. For every number this increases, this doubles. This 8, 16, 32, 64, and so on. So this grows very rapidly. We could also try negative numbers. If you go to the negative side of the x-axis, then we have 2 power minus 1. That's a half. This is a half. And f minus 2, then we have 2 raised to the power minus 2. And that's this, and that's a fourth. And so on. to the power minus 3 is 1/8. Then of course we could also try other numbers. For example, if you take a half, what is 2 raised to the power of a half? And that is square root of 2. And square root of 2 is roughly 1.41 if you take 2 decimals. Or if you like 3 halves, 2 raised to the power of 3 halves. And what's that? Yeah. Put into calculator, we see that this is equal to 2.83 roughly. And so on. So we can calculate this function for any x. And if we plug them in to a table and make a graph, you will have the examples we just saw in GeoGebra. To show an example of how fast an exponential function grows, let's again take this example 2 to the raised power x. For example here, if we start with one raising, and we put on the next square of each square of the chessboard, we double that amount. So under this we put 2, and here we put 4, and 8, 16, 32. So what did I say now? 16, 8, and 8 here, and so on. How many raisins will I have here on the last square if I double each time? Okay, so on the first square I will have 2. I start with 1, then I double to 2, so 2 to the power 1. Next square I have 2 to the power 2, and then a third 2 to the power 3, 8, and so on. So on the final square I have 2 to the raised to the power of 64. And how many raisins are that? Yeah, this is roughly equal to 10 to the power of 19 raisins on this. If I pack them here in a layer, all the raisins here in a layer, and I make a pile of them, how high a pile will this become? So what will be the height of this pile? Yeah, if you do rough estimate, the height of this pile will go from Earth outside the solar system. So extremely high pile of raisins. And that's the reason we see that the exponential function grows extremely rapidly. So although we only have a 2 here, and also the fairly modest 64, so 2 raised to the power 64 gives an enormous amount of raisins, or an enormous number. So 1 followed by 19 zeros. So an exponential function grows rapidly. So as another example, for example, if a bank gives you interest on what the money you have put into the bank. So let's say it gives you 3% interest per year of what you have put in. So let's say you have put in $100. How much do you have after 1 year? Then you have 100 times 103% of that, or you multiply it by 1.03 since it increased by 3%. So after 1 year you have $103. How much do you have after 2 years? Yeah, after 1 year you had this much. And then on the second year, this amount will increase with this much. So on your after 2 years you will have this much. And how much is that? And this is roughly, it's actually exactly equal to $106.09. And then after 3 years, then of course you will have raised to the power 3. And then after n years, or x years, you will have 100 raised to the power of n. So you see here we have an exponential function. So interest on what you put into a bank will increase exponentially. So for example, after 10 years, you will have raised to the power of 10 here. And how much is that? This is roughly 134. So you can't just simply add a percent, okay, like 3% per year, and 10 years, 3 times 10, that's 30%. The increase is more. So it's 34% increase after 10 years. And it's because you have exponential growth. So in this case, the growth is not so large, but because we haven't gone so far on the number of years here. So if, for example, if we instead go 100 years, or of course increase the starting capital, but if we go for 100 years instead, how much will we have then? Then this will be 1,922 roughly. So a naive estimate would maybe think that, okay, it's 3% per year, and 100 years is increased 300 times. So you would think that maybe you got if you increase like 3% per year, then 103 and then 106 and so on. So then you could think that you could end up with 400 or something, but the growth is much larger than that. It's exponential growth. Okay, so these are exponential functions. So this is an exponential function since it's a form of c times, here is 1.03, that's the number a, and this is the variable. So this is an example of an exponential function.